Okay, so it's been a few days since I recorded the last one, but let's go ahead and talk about how we can do some basic face space projections using the Eigenfaces example, and I am actually going to end up using the database that Stephen Brunton provides in his book, Data-Driven Science and Engineering, and you can find his datasets at databookuw.com. I don't know, I'll put a link. Anyway, so this dataset that he uses isn't necessarily his own. This is actually the Yale Faces dataset, and is fairly standard. You can go and try the same example and try the same methods in Kaggle with the Kaggle dataset, and I'll send a link to that too. It's just a massive dataset, and it'll take a long time to process. So just for us in this YouTube video, let's just stick to the basic faces, which are 192 by 168. And so, or actually, that's backwards. So MATLAB will list the rows first and then the columns. And so, but in typical images, typically when we talk about images, we talk about width and height. So as far as the image is concerned, this is 168 in width and 192 in height. So it's a little bit taller than it is wide. And this differs from what we see in the Eigenfaces for Recognition paper, where they had 256 by 256 images. So why don't we go ahead and jump into here, and I'm going to show you an example decomposing my own face and sending it to face space, where space depends on the data set that you use, but it gives you a whole bunch of weights that act as sort of a fingerprint for your face according to those faces that you encoded and that you extracted, these eigenfaces from the SVD or PCA, however you wanted to talk about it. So what we're going to do is we're going to take a look at these eigenfaces. We need to take an average of all the eigenfaces, and then we're going to subtract that off, and then we're going to perform the SVD. This is technically the procedure for doing the PCA, but it's still an example of SVD, and we'll talk about the PCA more properly later. I guess we should just go ahead and jump into it. The microphone, so it's a little bit more in line. There we go. Okay, so let's go ahead and take a look. I have in here. Is it recording? Yeah. Okay, so here I've taken a screenshot of something from the video that we just watched. So it's kind of blew up kind of large. Yeah. So this is a still frame from that video. And basically what I'm going to do is I'm going to make a selection, and I'm going to crop it, and then I'm going to resize it. And so this can all be done with basic imaging tools. This is just using Preview on my Mac. So this is ultimately the sort of thing we're dealing with. But honestly, it didn't look quite close to the images, and I'll show you what I mean in a second. So I did a little bit more cropping, and I got it down to this. And so I basically cut it down to almost where my eyes are. I chopped off most of my hair and a little bit of chin, but then if you look at this, the image itself ends up being a little bit larger than what we wanted. So we have a 235 height here. Anyway, so you can basically get your data into here pretty quick just by dragging and dropping right into the workspace. I already did that, and this is what gave me this C data. And so if you want to see what your C data looks like, you can do something called image show. You can see I've already done a little bit of testing with this. And so I can say C data, but C data itself is 235 by 168 image, so 235 in height according to MATLAB, and 168 in width by 3. Now where does that 3 come from? Well, we know that images are encoded in red, green, and blue. So with each of these are a different channel. What we're going to do is we're just going to use one of these channels, and two seem to look the best. So what I'm going to do is I'm going to take C data. I want all the rows, I want all the columns, and I am going to just take the second channel. If I didn't include this here, then it would sort of it might look oversaturated, and so when you give this little empty block here, empty matrix, it tells it basically to go ahead and just retune the maximum and minimum so it fits as an image. Because basically image values should range between 0 and 255, but sometimes MATLAB might have a number like 1000 or something like that, and they'll just appear as white on the image. So here we're just going to put this, and I think it should work. There we go. So here we go. That's my face, and that's what we're working with. Now again, this is a little bit taller than what we wanted, and so if you look inside here, after I load my face from the C data, and I extract only the second channel, I also only extract the first 192 rows. So this basically says take all the rows from 1 to 192, but keep all the columns. So then that basically effectively does a crop in MATLAB, and now it fits the size of the image space. So what are the images that we're working with? So this is, I loaded faces from the data set, and if we take a look, faces itself, it's 3,256 by 2,410. That is definitely not the image size. That would be a really big image. So how does that really break down? Well, if you look in here, we try to factor, well, okay, I'll just give it to you straight. So 32256 divided by 192, guess what? That is 168. So what we've done, what they did is they took all of the images, and they took the two-dimensional image, and then they reshaped it. This reshape command is basically like this. So if you take an image, any sort of matrix, let's say 1, 2, say 3, 4, 5, 6. So this is a matrix. It's encoded now as the variable answer, and I say reshape, and I'm going to take the answer matrix, and then it wants you to know what sort of dimensions to give it. So I'm going to say I'm not going to define how many rows, but I want as many rows as it takes to keep everything in one column. And so what does it give us? It gives us this. So it just takes this guy and just moves it underneath here, but it more or less keeps the order. So that's what you need to do with the face data that I just loaded. And so here I have my face data, the 192 by 168, and only the second channel. So that's now a matrix, and I want it as a single vector. So that's what this is. I'm saying it to reshape my face data as many rows as it takes, but just one column. And then finally, I change it to double, and that's just a variable type issue, so we can do matrix manipulations and stuff like that. So it's not just integers or other things like or text data. It becomes proper number of values. So all right, so that's what we got there. Now let's take a look at the faces. We can see a couple of faces right from the beginning. So if we take faces, and I take a look at all right, let's see. So I'm going to do what I said before. I'm going to say image show. Let me make sure I don't have an active figure. No, okay. So I have image show, and I'm going to reshape faces, but I want, say, the first face. So I'm going to take everything here, but the faces are ordered in a whole bunch of columns, one after another, and so I'm just going to take the first row here and that column, but now we want to actually reshape it as 192 by 168, and then rebalance the value so it fits inside of an image. And so we'll go ahead and do that. So that was a reshape there, and now the value is there. Okay, and so now I'm gonna go ahead and play it. All right, that's our first image. Okay, now I can say if we want to see what another one of the faces looks like, I can select the 1000th face, and that it seems to be a very dark image. So it looks like they tried a whole bunch of different images with different lighting and different value. And so we can go and try, say, another 2000. There's a lot of faces in here, and that's another one. And so, so these are the faces that are being used to make our eigenfaces. So, so then what do? Well, first, what we need to do is we need to go ahead and take the average of all the faces. And so let's go ahead and run this bit of code independently. It might take a little bit, but let's see what happens. So I'm going to take the average faces, and didn't take that long. And now let's take a look and see what these look like. I'm going to take average faces, and I'm going to put it in here, and let's see what we get. And there we go. It's sort of a, it looks like a face, I guess. I mean, that's all it takes. So that was the average over all 2,410 faces in the database. All right, so now what I'm going to do is I take the faces and I subtract the average faces. This is actually the first step in PCA. PCA is a lot like singular value decomposition in that singular value decomposition tries to find the best orthogonal directions to describe your matrix, but for PCA it's not just a matrix, it's actually a data set. And so you might have a whole cluster of data off in the middle of nowhere, and you want to get that back towards the origin, so when you talk about the orthogonal directions, they actually make somewhat sense. So, so then what you do is you just take that cluster of data, wherever that is, you take its average, and then you shift it back to the origin, so now you can be somewhat assured that you're actually in the middle of your data set before you do the SVD and find these principal directions. So, so then that's what we do. SVD, normalized faces, and so then so we get here. Now this is going to take the most time of everything we're doing here, and so I can go ahead and evaluate this selection. I'm just doing this sort of piecemeal. If I just run the code, it'll do everything for me, but let's just see what ends up happening. So this is going to take the longest amount of time because we're basically trying to do an SVD on a matrix that is fairly large. The ultimate result is that the U matrix is going to have the same number of rows as each one of our faces, and so that's actually going to end up representing our eigenfaces, and so we'll end up doing a reconstruction of, say, my face, or the projection of my face onto these eigenfaces, and that'll give us sort of our transformation. So, so it took 36 seconds, and through me jabbering, to do this. And so let's go ahead and take a look at the first several eigenfaces. And so here I just made it code to pause for 1/10 of a second, and then just show each eigenface. So again, we're running through all these U's, and each column of U, which is indexed by I, so I take all the rows of that column, ends up being an eigenface. And so I go ahead and evaluate this, and let's see what we find. And so these are the eigenfaces that we end up determining. So these are like the first 40 like really important faces that we wanted out of here. And so what we can do is I can say, so that's the data loading my face, and I think we've already loaded that, but we can just go ahead and do this, talked about it already. So that's loaded, and now this is the code that ends up projecting my face onto the eigenfaces. So first what I need to do is I need to take the data that came from my face, which is a column, and I need to subtract it from the average faces. So this is sort of a renormalization. And so then I take this difference, and then I multiply by U prime, where I only take the first 40 U's because these are going to have the most variance of all of the data, and the idea is that higher U's will end up only reflecting noise and other things like that. For more and more complicated, the more and more your image differs from a face, the more of these basis functions you'll need in order to describe it. Whether you want to describe a teacup, like what Stephen Brunton does in his book, or a dog, and yeah, you can actually take an entire movie and describe it in terms of eigenfaces. It might look weird at a few places, but might maybe have eyeballs appear in a weird scene. But that's that's actually something you can do. So this is a projection onto the force 40, and so this will end up giving me my weights. So if I go ahead and evaluate this selection, and so let's take a look and see what the weights are. First of all, let's see the size of W. So basically, this basically says that so this weight vector is actually my projection onto the eigenfaces. This is my face transform, the eigenface transform to face space. And so each one of these values basically gets slapped onto a U, and once it's slapped onto a U, you can sum up all those U's, and you should get an approximation of my face. It may or may not be a good approximation with only this first 40, but it'll get you started. And it turns out for facial recognition itself, you might not need to be able to reconstruct the face exactly, but you could use, say, the first 40 as sort of an identifier. And so this becomes my face fingerprint, or my face print, according to these eigenfaces. And so then you can compare this face print with another face print and see how close they are, and make a guess as far as how similar that new face is that you're looking at is to an old face that you've already encoded. And so the idea is that you could take a whole collection of different faces from different people and make what we would call a support vector machine classifier or a multi-class classifier, and then you basically try to use that information in order to classify a face as belonging to one person or another. Here we only have the data from my face, so we're not going to make a facial recognition software, but that's how basically this is the first step of how you do it. You encode into this face transform, and then you no longer have to store the all the 192 by 168 information that comes from a single person. All you need to store is the first 40 values that you get from these eigenfaces. And if that ends up not giving you a very good one, then you can increase it to maybe 50 or to 100, but it's still dramatically less than what you would be getting, what you would have to do by storing all of the face data, all the pixel values from that single picture. So let's go ahead and take a look and see exactly how good it did. I seem to remember it's being pretty terrible. So what you can do if you want to reconstruct it is from these W's is you take this U and you multiply it by a W. And so basically, if you remember your matrix multiplication, a matrix times a vector basically is a linear combination of all the columns from that matrix weighted by the weights in the vector. And so that basically does this eigenface reconstruction right here. So then we can go ahead and we run this, and then I can go ahead and show you the picture. I think it looks pretty horrific, but yeah. So this is the eigenface approximation of me using only the first 40. Terrible approximation. I mean, if you don't remember what my face looks like, let's go ahead and load that in. So we can say image show. We'll do C data, take all the information there, take 2, and there. So boom. And so that's what my face looks like. And that looked nothing like, what we got here. Shoot. So here we go. So my face, the approximation of my face. You can kind of see the nose is in the right spot and the eyes are kind of making out. Okay. That you can kind of see is trying to get something with my glasses here, I think. It seems kind of like it's starting to get there. A lot of the values in the right spot. Remember, I did truncate it, so I did chop it off here. So a lot of things are right. I mean, like the lips are a little bit bigger than my lips, but it seems to have the lips in the right place. And so if you want to see what happens if you increase it from, say, 40 to, say, 200, let's see if we get a better approximation. It shouldn't take too long. Let's see what we get. So evaluate. And now it looks like a mess, but it is a little bit closer. And let's take it up to, say, 500 if we really want a proper view approximation of my face. Let's see. Now you can actually see things are starting to really come out here. It's a figure, and let's go back to see there. Okay, so So now you can see it's starting to really come together. The lips, more or less there. The nose is starting to come together here, and then you can start seeing my eyes pop out here. Let's take it up to 1,000. You notice that it doesn't actually take all that long to do all these estimations. And so, let's see, evaluate selection. There you go, it's starting to come really together now. Let's see, figure, show, there you go. Need to stop closing a second figure. And so then you can really start seeing things to come together. And if I really want to include everything, I can take it up to, say, 2,000 and 2,000. But this isn't really in the spirit of the facial recognition anymore. It's more of an approximation. And so here we go. Let's see what we get. Oh, what happened? Incorrect matrix multiplication. Should be fine. What'd I change? Yeah, that's all I changed. Let's see. 1,500. Let's try it. Alright, and 1,500. There we go. Alright, let's do it. Let's see what we get. Choop. There we go. Alright, so it's getting better and better. And then should be able to go all the way up to more than that. Let's see. What is the size of you? Yeah, should be able to do a lot more. Oh, anyway. So that gives you an idea. Let's go back just to the first 40. And so we're trying to do image. We're not trying to build the face back, but we're trying to use, this. We're not trying to make the face again. We're trying to use this for facial recognition. So we just need the first several variances and encode those as our from the face itself, and then that is really what it gives us here. So yeah. Anyway, so that's Eigenfaces, and that's how you work with it. And so if you haven't messed with MATLAB here, hopefully this gives you a better idea. I made the window a little bit smaller, so maybe it's a little bit easier to read now. But yeah, this is Eigenfaces, and this was also really kind of the PCA, which is a step above just doing the SVD. But you can see numerically it doesn't really make that much of a difference. So at this point, I think I should stop and let you go. And yeah, thanks for watching.